In this video, we'll explore the dot product of vectors. Now, the dot product is a way to multiply two vectors that result in a scalar, or a single number, rather than another vector. This is different from the cross product, which we haven't discussed in this course yet, but you may be aware of, where we end up with a vector from the product. Now, with the dot product, we're looking for the magnitude of how much one vector aligns with another vector. Anyways, that's one way to look at it. The way that I tend to kind of introduce the concept of the dot product to my students is you're looking for the product of the components of two vectors that are parallel to each other, not just the product of the magnitudes of the vectors, specifically the product of the parallel components of your vectors, okay? And we do it just by making one vector parallel to the other vector using cosine theta. I'll explain a little bit more. But first off, I want you to take a look at the two vectors that are on the screen. We have vector A in blue, and then we have vector B in what's somewhat navy blue. Now, what I've labeled on the screen are the coordinates of the terminal point of vector A and the coordinate of the terminal point of vector B. And if each of these vectors is starting at the origin, has its starting point at the origin, then these values of these components should be the horizontal and vertical components of the vectors. All right. And so when you know the horizontal and components, the horizontal and vertical components of your vectors for both of them, it's really, really easy to take the dot product because you can follow this mathematical equation right here. It's that the dot product of two vectors A and B, if you know their components, is the product of their horizontal components plus the product of their vertical components. This is a really simple way to quickly calculate the dot product. And remember, this result is not a vector, it's just a scalar. It's just a value. But to go along with what I was discussing before, another mathematical equation that can be used to find the dot product that really effectively models dot product is what you see here. Now, it's also the dot product of vector A and B, but what it's telling you to do is it's telling you to take the magnitude of vector A and the magnitude of vector B as well as cosine theta. Now, what multiplying the two magnitudes, the product of the two magnitudes by cosine theta is going to essentially align the two vectors. Let me kind of show you what I mean, all right? So if you have essentially vector A projected onto vector B, we're going to discuss projection a little bit further in the next video actually, but if you literally just projected A onto B and we were just looking for the portion of A, the component of A that is parallel to B, all right, then you're gonna get that orange arrow by multiplying the magnitude of A by cosine theta, where theta is the angle in between the two vectors. That's gonna give you that orange vector, and then we're gonna multiply that magnitude by the magnitude of vector B, all right? It also works the other way around, and because the result is just a scalar, it actually doesn't matter which one. We have a commutative mathematical model here. It doesn't matter which vector we multiply the cosine theta by. So that's really interesting, all right? That said, let's see if we can look at a really simple example. Suppose we have the vectors A and B, where A can be expressed as negative 2i hat plus 3j hat, and B can be expressed as 7i hat minus 5j hat. The question says, find A dot B. Well, we just got introduced to this really simple mathematical model that said that A, vector A dotted with vector B, is actually equal to, and if I take the horizontal components here, it's equal to the product of negative 2 and 7, all right, the product of negative 2 and 7 plus the product of 3 and negative 5, all right? If I do that in my head really quickly, then what I have is negative 14 plus negative 15. And another quick little bit of work in your head gives you negative 29. So negative 29 is the dot product of vectors A and B. Now let's take it a little bit further. Given what we know here, can we find the angle between the two vectors? Yeah, well, we definitely can. It's going to be a little bit more work, but we do have a math model for dot products that allow us to find the angle, or at least that has the angle in it. So let's see if we have enough information. Let me switch over to green. And let's say that the math model that I was referring to just now is the dot product of A and B is equal to the magnitude of A times the magnitude of B times cosine theta. Now, we're not given the magnitudes, but in this first part, we were given the components. And if we're given the components, then we can quickly find the magnitude just using Pythagorean's theorem. That said, we'll have to find the magnitude of each vector, and then we're going to use what we already know about the dot product to find cosine theta. In other words, I'm going to plug that negative 29 in for A dot B, and then I'm just going to go ahead and quickly, and I'm going to do this in purple for each one of these really quickly. I'm going to find their magnitudes. So I'm going to say that the magnitude of vector A is equal to the square root of negative 2 squared plus 3 squared. And then I'm going to say that the magnitude of vector B, is the square root of 7 squared plus negative 5 squared. All right, and I have that the magnitude of each of these when I plug them into the calculator is root 13 and root 74. And I'm not going to bother with taking approximations of those irrational numbers. I'm just going to keep them as is, and I'm going to say that that root 13 is the magnitude of vector A and that root 74 is the magnitude of vector B. And I'm going to plug them in right here. I'm going to keep the purple down here on the bottom of the screen. I'm going to say that negative 29 is equal to root 13 times root 74 cosine theta. All right, hopefully you can see a clear path to solving for theta. Let's go ahead and work it out together. First thing, I'm going to do one inverse operation where it's going to be moving those roots, those radicals, to the other side. So it's going to be negative 29 over root 13 times root 74 is equal to cosine theta. And from here, there's a little trick that you may or may not be aware of. And it's that if you know what cosine theta is, all right, if you know what cosine theta is equal to, then you can take inverse cosine of what that's equal to and set it equal to theta. All right, let me show you exactly what I mean. I can say that, and I'll do this in red, that cosine inverse of what I have over here just right, of what I have just right here, cosine inverse of negative 29, all right, over root 13 root 74, all right, is equal to theta. And if I plug that into the calculator, assuming that we have a scientific calculator available to us, then that's going to come out with something that's very similar to 159 degrees. All right, 159 degrees, and that means that like these two angles, just a quick sketch here, are going to make like a pretty big angle with each other. All right, that's a rough and ugly sketch, but let's actually graph it and see what it looks like. So keep this 159 degrees in mind. All right, and I'm going to graph it using these values. So let me copy these. Let's copy. Come down here. And I'm just graphing to see if what we got is reasonable and makes sense. Okay, so let's go ahead and draw a grid here really quickly. And starting from the origin for each vector, I'm going to do green, vector A in green and vector B in blue, just so it's consistent with what you see written at the top. If we have negative 2, positive 3, then that's going to look like negative 2, positive 3. It's going to look like a vector right here. Negative 2, positive 3. This is what vector A looks like to me. Starting from the origin, that comes to the point, the terminal point of negative 2, comma 3. All right, and then for B, we have 7, negative 5. Okay, so 1, 2, 3. Let's switch over to blue. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. All right, so that's going to be this vector here. Oh, 1 second. I said positive. I was starting to wonder. I was like, wow, that looks like 90 degrees almost. That's not quite right because I made a mistake. It's going to be 7, negative 5. So 7, comma, negative 5. So 7, comma, negative 5. This is going to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. This is the point we're looking for. And that's making a lot more sense to me because I know that my vector is actually relatively close to 180 degrees. It's less than 180 degrees, but this vector here, based off of what we calculated doing the dot product, should be something close to 159 degrees. 159 degrees. And that looks like it very well could be about 159 degrees. I'm just happy that our graphical what we plotted here on the graph is going to be checking out with what we calculated, That makes me feel comfortable. Hopefully that makes you feel comfortable with the understanding. Just keep in mind that there's these two math models to go off of based off of what you're given in the problem. Good luck, and I'll see you in the next one.